In this video, we're going to look at how to sketch functions so that when you're given something like this, you'll be able to draw it yourself, just like a graphing calculator would. It looks worse than it actually is, I promise. The good news? I'm going to give you a simple action plan to follow. And even better news? If you've made it through the videos up to this point, you already have all the math tools you need to do this. You'll see, this is the moment where everything you've learned so far finally comes together. So let's jump in and start with our game plan for sketching functions. Our action plan is going to follow 4 steps, and we're going to do them in this exact order. If you stick to these 4 steps, you'll see just how manageable this really is. Step 1 is to find the x and y intercepts. In other words, figure out where your graph will cross the x-axis and y-axis. Step 2 is to identify any discontinuities. Don't stress if you're not sure what that means just yet. We'll go through it together when we get there. Step 3 is to find any horizontal asymptotes. And finally, step 4 is to find the first and second derivatives and understand what they tell us about the shape of the graph. All right, let's dive in. Right, let's kick off with step 1. In this step, we're going to find where the function cuts the x-axis, called the x-intercept, and where it cuts the y-axis, called the y-intercept. Finding these points is actually super easy because the process is exactly the same for all functions. If you want to know where the function cuts the x-axis, you simply set y equals 0. That means wherever you see a y in your function, you replace it with 0 and solve. All right, so we take our function equation and we substitute y equals 0. Next, we try to factor wherever we can. In the numerator, we can factor out a 3 as a common factor, and we're left with a difference of squares. In the denominator, we also spot a difference of squares. Now when we look at both, we notice that none of the brackets are the same, so nothing cancels out. Here's the important part. We're only interested in where the numerator is equal to 0, because remember, the denominator can never be 0. We're not allowed to divide by 0 in math, so we ignore the denominator, set the numerator equal to 0, solve, and we get our answers. That means the function will cross the x-axis at these 2 points. Now for the y-intercept, meaning where the function cuts through the y-axis. The rule is simple. If you want to know where a function intersects the y-axis, you just set x equals 0. So wherever you see an x in the function equation, you simply replace it with 0, simplify, and this is the answer you get. That means the function passes through the y-axis at this point. With the answers we've just found, we can now start building the shape of the function. We now know where the function cuts through the x-axis, and we also know where it cuts through the y-axis. So the next step is simple. We plot those values straight onto our sketch. That gives us a solid foundation to start drawing the rest of the graph. And with that, we've completed step 1 of our action plan. To summarize, in step 1, we figured out where the function crosses the x-axis and the y-axis. To find where it crosses the x-axis, we set y equals 0. To find where it crosses the y-axis, we set x equals 0. Simple, consistent, and it works every time. All right, now let's move on to step 2. Now in step 2, we're going to identify any discontinuities. So, what exactly is a discontinuity? A discontinuity is basically a point where something goes wrong in a function. At a specific x value, there's a problem that causes the function to not exist there. We get 2 types of discontinuities. 1. Removable discontinuity. In plain English, this means there's a hole in the graph. At that specific x value, the function just doesn't exist. There's a little gap or missing point. 2. Non-removable discontinuity. This happens when there's a vertical asymptote. And we already know, an asymptote is like an electric fence. The graph can't touch it, and it can't cross over it. So now the big question is, how do we know whether a function has a hole, an asymptote, or neither? Let's look at how to figure that out. So now we understand that a discontinuity is when something goes wrong at a specific x value in a function. The next question is, what in math actually causes these issues? Well, there's one thing that always causes problems, and that's dividing by 0. So whenever we have a function that's written in fraction form, we already know there's potential for an issue. Because if the denominator, the bottom of the fraction, becomes 0 at any x value, then the whole function breaks down right there. So discontinuities happen when a specific x value makes the denominator equal to 0. And that's what we're going to look for. Now that we know what causes a discontinuity, the next question is, how do we know whether it's a whole or a vertical asymptote? The good news? It's actually really easy to figure out. You just need to ask one simple question. If we factor the function and the denominator cancels out, then it's always a whole. But if we factor and we can't cancel out the denominator, then it's a vertical asymptote. That's it. Easy rule, and it works every time. All right, let's go through two quick examples together to really make sure this concept is clear. Example 1. We are given the following function. The first question we ask is, does this function have any possible discontinuities? When we look at the function, we can see it's a fraction, and we know that if the denominator equals 0, it will cause a discontinuity. So our answer is yes. This function does have a discontinuity. Now the next question is this discontinuity a whole or a vertical asymptote? To figure that out, we ask one simple question. Can we cancel out the denominator after factoring? If yes, then it's a whole. If no, then it's a vertical asymptote. So let's factor the function. When we do, we see that we can cancel out the denominator, which means this discontinuity is a whole, and it happens where the function has an x value of -3. So wherever the graph of the function lies, we now know that at x equals -3, there will be a whole, because when x has a value of -3, the denominator becomes 0, and that's exactly what causes the function to break at that point. Example 2. In this example, we can once again see that there are possible discontinuities because we're working with a fraction, and we know the denominator can't be 0. So at any x value that makes the denominator equal 0, we're going to have issues, in other words, discontinuities. Now the question is, are these discontinuities wholes or vertical asymptotes? To figure that out, we ask the same question as before. If we factor and the denominator cancels out, then it's a whole. If we factor and can't cancel the denominator, then it's a vertical asymptote. So let's factor the function. After factoring, we get the following expression. And we can see that none of the brackets are the same, so nothing cancels out. And that tells us we're dealing with a vertical asymptote. Now, where exactly do these asymptotes lie? They lie at the x values that make the denominator equal 0, because that's where the function breaks. So we take the denominator, set it equal to 0, solve, and the answers we get are the x values of our vertical asymptotes. The graph will never touch or cross these lines. Now that we understand what a discontinuity is and how to identify them, let's go back to the function we've been sketching and figure out whether this function will have any discontinuities. So when we look at our function, we can immediately see that it's written in fraction form, which means we're going to have discontinuities. These discontinuities happen at the x values that make the denominator equal to 0. Now we need to figure out whether these discontinuities are wholes or vertical asymptotes. And to do that, we ask one key question. If we factor the function and the denominator cancels, it's a whole. But if we factor and the denominator doesn't cancel, then it's a vertical asymptote. When we factor the function, we get the following expression. And right away we can see none of the brackets are the same, so nothing cancels out. That means our function has vertical asymptotes. Now we need to determine exactly where those asymptotes are. To do that, we take the denominator, set it equal to 0, and solve, because discontinuities happen where the denominator becomes 0. When we solve that equation, we get the answers. These are the x values where the vertical asymptotes of our function lie. Now we're going to plot those asymptotes on our sketch. And as we move through each step of our action plan, we're going to add each new answer to our graph. And slowly but surely, we're building the full shape of the function. This brings us to the end of step 2, where we've successfully found and analyzed the discontinuities. Let's quickly summarize step 2, where we looked at discontinuities. In this step, we saw that if a function is written in fraction form, we can expect discontinuities, which are x values where the function simply doesn't exist. These discontinuities are caused when the denominator becomes 0, because we know in maths we can never divide by 0. We identified two types of discontinuities, and to figure out which one we're dealing with, we always ask the same question. If we factor the expression and the denominator cancels, then we have a hole in the graph. But if we factor and nothing cancels, then we're dealing with a vertical asymptote. Now for step 3 in our action plan. In this step, we're going to determine whether the function has any horizontal asymptotes. So how do we do that? Let's break it down clearly and step by step. What is a horizontal asymptote? We already know that an asymptote is like an electric fence, something the function cannot touch or cross. We've just dealt with vertical asymptotes, which are vertical lines the function cannot go through because of discontinuities. Now we are going to see that some functions also have horizontal asymptotes. These are horizontal lines that the function cannot cross. This happens when, as the function keeps going forever to the right or to the left, we notice that there is a certain y value it just cannot pass. That y value is the horizontal asymptote. In formal maths terms, we say the function converges to a specific value, meaning it gets closer and closer to a certain number, but never quite reaches it. So how do we calculate this value? In other words, how do we figure out whether a function has a horizontal asymptote? Here we bring back our good friend limits. To find where the asymptote lies, we calculate the limit of the function as x approaches infinity, both positive and negative infinity. Why both? Because we want to know if, as the function goes off forever to the right, positive infinity, or forever to the left, negative infinity, there's a specific y value the function is being pulled toward, a value it gets closer to, but can never touch or cross. That value is our horizontal asymptote. Luckily, we have already covered limits to infinity in earlier videos, where we worked with rational functions using our chocolate sharing fractions method. If you have forgotten that a little, please go back and rewatch that video, because we are going to use the exact same steps here. So in short, when we have a rational function, which means a fraction with x in the denominator, our first step is always to divide every term by the highest power of x in the denominator. In this case, we can clearly see that the highest power of x in the denominator is x squared, so we divide everything by that. Next, we simplify, and that gives us this new expression. After that, we substitute in infinity and start looking for chocolate sharing fractions. A chocolate sharing fraction is any term where we divide a number by infinity. In this case, we see that both the numerator and the denominator contain chocolate sharing fractions. These terms where we divide by infinity always become 0, so we replace them with 0, simplify again, and then we get our final answer. Here, the final answer is 3. That means the horizontal asymptote lies at y equals 3. Look carefully. In this example, it does not matter whether we approach positive infinity or negative infinity. We get the same result both ways. So we can say that as the function goes off to both the right, positive infinity, and to the left, negative infinity, we still end up with the same horizontal asymptote at y equals 3. This is important because there are functions that have different horizontal asymptotes on the right-hand side compared to the left-hand side. In these cases, you will get two different answers when you calculate the limits. The limit as x approaches positive infinity will tell you where the graph levels off to the right. The limit as x approaches negative infinity will tell you where the graph levels off to the left. So always check both sides when looking for horizontal asymptotes. So in our function, both positive and negative infinity give us the same value, which means we have one horizontal line at y equals 3. That brings us to the end of step 3. The only thing left now is to add this result to our sketch, and then we are ready to move on to our fourth and final step. Let's do a quick recap. In step 3, we determined the horizontal asymptote of the function. A horizontal asymptote is a horizontal line that the function cannot cross as it goes off forever to the right, positive infinity, or to the left, negative infinity. To find this asymptote, we used limits, specifically the limit as x approaches both positive and negative infinity. To calculate limits to infinity, we use the chocolate sharing method, just like we explained in previous videos. The answer we got from that process gave us the equation of the horizontal asymptote. Before we move on to step 4, there are two important side notes about horizontal asymptotes that confused me as a student, and I want to touch on them quickly. The first one is, when do we know a function does not have a horizontal asymptote? This is actually very easy. A function will not have a horizontal asymptote when, as we take the limit to infinity, the answer is positive infinity or negative infinity. Positive infinity means the function keeps going up forever. so its y values keep increasing without bound, and there is no specific y value it approaches. It is the same with negative infinity. If we get that as the answer, it means the function keeps going down forever, so its y values keep getting smaller without bound, and it does not converge to a specific y value. So if you get a nice, solid finite number when you take the limit to infinity, then the function has a horizontal asymptote at that value. But if your answer is infinity, positive or negative, then that function does not have a horizontal asymptote. The second thing that also confused me about horizontal asymptotes is that we know an asymptote is a line that a function cannot cross or touch. But this is not completely true when it comes to horizontal asymptotes. A function can cross a horizontal asymptote in the middle part of the graph because the asymptote only comes into play as we move forever to the right, positive infinity, or forever to the left, negative infinity. So as we stretch the function out toward the ends, it cannot cross that asymptote there, but between those ends, there are functions that can. This is just an important side note to remember. Now for the final step in our action plan, and that is to find the first and second derivatives, and to understand what these derivatives tell us about how to finish sketching the function. Ready? In this step, we're going to find the first and second derivatives, because these two things will determine the shape of the graph. In other words, how to draw the function. So let's jump right in and start differentiating. Very important, you should first watch the videos on how we differentiate any equation using our three-step game plan before continuing here. Because in this video, I'm not going to re-explain the differentiation process. The video is already long enough, so make sure you know the game plan. Split up, set up, and differentiate. When we differentiate the function for the first time, we get the following result. Pause the video now and make sure you get the same answer. We now have the first derivative, which means we've differentiated the function once. In step 4 of our action plan for sketching functions, we also need to find the second derivative. To do that, we take the result from our first differentiation and differentiate it again. When we do this, we get the following result. Pause the video now and make sure you get the same answer for your second derivative. Now that we have the first and second derivatives, how do we use them? When we set the first derivative equal to 0, we find the turning points of the function. This is because the derivative gives the slope, and at a turning point, the slope is horizontal, which means the slope is 0. So setting the first derivative to 0 tells us exactly where those turning points are. Let's do that now. We take our first derivative and set it equal to 0. With a fraction equal to 0, we only focus on the numerator and set it equal to 0 because the denominator can never be 0. We cannot divide by 0. This is the x value of the turning point. To find the y value, we substitute our answer into the original function. This gives us the y-coordinate, and together they form the turning point of the function. We can now plot this turning point on our sketch. So we know that on our sketch there must be a turning point exactly at this position. Now for the second derivative. When we set the second derivative equal to 0, we get something called an inflection point. So what is that? An inflection point is a point on a function where the function changes its concavity. In plain English, an inflection point is where a function changes from a frown to a smile, or from a smile to a frown. It's an important point because it marks where the overall shape of the graph changes. We calculate this point by setting our second derivative equal to 0. When we do this, we once again focus only on the numerator of the fraction and set it equal to 0 because we know the denominator cannot be 0. When we do this and solve for x, we'll see that to get rid of the square, we use a square root, and our answer ends up being a negative number under a square root. When that happens, a negative number under a square root, there is no real solution. So in this case, we can conclude that the function has no inflection points. If you did get a solution here, you'd just do the same as with the turning point. Plug that x value back into the original function to find the y value of the inflection point. We've finally reached the point where we can sketch the function. We've already worked out all the key features using our action plan, so now all that's left is to draw it. But how do we know what goes where? For example, let's say we start on the left-hand side of the graph. We can see we've got a horizontal and a vertical asymptote, but how do we know if the function sits above or below those lines? How do we figure that out? To figure out the shape of the function, we use something called the derivative number line. Here's how it works. We only draw the x-axis, nothing fancy. On this number line, we plot the x values of the important points we found in step 4 of our action plan, specifically the x value of the turning point, the x values of any inflection points, and the vertical asymptotes. Important, we only use the x values, not the full coordinates. In our case, the turning point had an x value equal to 0. The inflection point had no real solution, so there's nothing to plot there. And don't forget to include the x values of the vertical asymptotes, because those are places where something weird happens, a discontinuity. So if we plot everything on our number line, we'll mark x equal to -5 for the first vertical asymptote, x equal to 0 for the turning point, and x equal to 5 for the second vertical asymptote. This number line is now ready to help us test the function's behavior between those key x values. Now for the next step of our derivative number line. We are going to add the first and second derivatives to it. What we want to do now is plug in values into the first and second derivatives that make sense based on our number line. So for the first interval to the left of -5, we can use x equal to -6. We substitute -6 into both the first derivative and the second derivative, and we write down whether each answer is positive or negative. That is all we care about, the sign, not the actual number. Next, we choose a value between -5 and 0. So let's go with x equal to -1. Again, we substitute it into both derivatives and record just the signs. Then for the interval between 0 and 5, we can use something like x equal to 1. Plug that into both derivatives and note the signs. Finally, for the last interval to the right of 5, we use something greater than 5. Let's say x equal to 6. Sub it and check the signs of both derivatives and write them into your number line chart. So what do all these signs actually mean for the shape of our function, and how does that help us draw the graph? Let's break it down. The first derivative tells us about the slope of the function. If the sign is positive, the function is increasing, which means it goes upwards from left to right. If the sign is negative, the function is decreasing, meaning it goes downwards from left to right. The second derivative tells us about the concavity or curvature of the graph. If the second derivative is positive, the graph is concave up, part of a smile. If it is negative, the graph is concave down, part of a frown. When we now add this information to our derivative number line, it gives us the perfect summary of what the shape of the graph should look like when we sketch it. So for our first section, up to -5, we can see the function has to move upwards and be part of a smile. The only way the graph can look here is like this, rising from left to right and curving upward. That immediately tells us the function cannot be below the asymptote in this region, because then it would have been decreasing and part of a frown. Also, remember, the function cannot cross any of the asymptotes. For the second part, between -5 and 0, the graph still moves upwards, but now it is part of a frown. We also know from our action plan that it must pass through x equal to -3 and then turn at the turning point we calculated earlier. In the next section, from 0 to 5, we see the graph moves downwards, and it is still part of a frown. We also know it needs to pass through x equal to 3, and again, it cannot cross the asymptote at 5. In the final part, from 5 onwards, the graph must go downwards and be part of a smile, so it needs to lie in this area to meet both conditions. And just like that, boom, you have successfully sketched the full function with all its components in place. All right, time for our final summary on how to sketch a function. In step 4, we found the first and second derivatives. Then we set each of them equal to 0. When I set the first derivative equal to 0, the x values I got were the turning points of the function. To find the corresponding y values, I simply substituted those x values back into the original function, and that gave me the full coordinates of the turning points. When I set the second derivative equal to 0, it gave me the x values of the inflection points, which are the places where the function switches from a smile to a frown, or from a frown to a smile. To find the y values, I just plugged the x values into the original function. After that, we used both derivatives to build a derivative number line, which helped us figure out the shape of each section of the function. Well done! If you have made it this far in the video, you now know how to sketch any function, just as well as your graphing calculator. If you want more examples, shortcuts, and easy-to-follow tricks, grab your copy of Calculus for a Student by a Student, the book that helps you actually survive calculus without losing your mind. Links down in the description. If this video helped, smash that like button. See you in the next one. Cheers!